All right, Chapter 6, Section 3. This is the Grandmaster video for domain and range. So we have a few critical thinking problems. The first one is an electric car can travel about 200 kilometers before its battery needs recharging. So it says, first, create a graph showing the distance traveled versus time if the car moves at an average speed of 60 kilometers per hour. So at time equals 0 hours, I haven't traveled any distance. So time is the independent variable horizontally. Distance is the dependent variable listed vertically. So I can plot 0, 0 right there. Okay. And at time equals 1, which means 1 hour later, well, I must have traveled 60 kilometers. Okay. So that would be right here. Okay. Now, the question says, this is my average speed. So since that isn't changing, this should give us a straight line. We hope. Okay. Time equals 2. Well, for every kilometer traveled, for every hour traveled, I travel an additional 60 kilometers. So this would be 120. All right, so where are we? Here. So we can see clearly that there is a straight line. Does that mean we should go up forever? Well, not quite, because we're told we can only travel up to 200 kilometers per hour, so we kind of hit a maximum here, so I'll just make note of that right there. So we're kind of restricted. Okay, this is a continuous relation, okay, because we can, of course, travel for amounts of time in between hours, so I'm just going to get the line going here. And let's draw a straight line as best we can. Something close to that. That's about as far as we can go. I don't know where that point is just yet, but I'll put it in there. All right, so create a graph showing the distance traveled. There we go. Okay, so it would be a mistake to have it going on forever because we can only go 200 kilometers before recharging. Okay, so number 2, it says, given that the car cannot travel more than 200 kilometers, which we know, before recharging, determine the domain and range of the above relation using, well, all of the notations that we've discussed. Okay, so I've actually already started that. Okay, I included the upper bound. Okay, we can't go higher than that. I'll just put this in here. This is the right bound. I don't know exactly where that is just yet. We'll figure that out. So obviously between 3 and 4 hours before we have to recharge. Okay, so we just need to describe the domain and range. And it might be useful to look at an equation. Okay, we know that distance is our speed times the time, our average speed. So that would be 60 times t. All right, so just make note of that. Might have to use that in just a sec. All right, so we're not dealing with x and y in this case. We're dealing with d and t. So, I don't know. Let's do the domain over here. Okay, and I'll do the range over here. Why not? Doesn't matter. There we go. Okay, well, I'm actually going to do the range first, because that's a little bit easier to determine just by looking at where those boundaries exist on the graph. So the range, we want, what's the first one? We want number line notation. Okay, well, our number line goes as far down as 0 and as far up as 200. So since we don't have a number line already, let's create one. I don't know, I'll put 0 here and put 200 here. I don't have to put all the numbers in between. Now, we're assuming that they're inclusive. So I'll put these dots there. So the car can travel anywhere between 0 and 200 kilometers without charging. Okay, so that's number line notation. And remember the range, the variable, that's the dependent variable, that's distance, so we're going to use d. Okay, so that's number line. Let's use set notation. So that would look like this. So the range is the set of all distances, d values, such that I'm larger or bigger than or equal to 0, but less than or equal to 200. And it is continuous, so d can be a real number. Okay. And interval notation couldn't be simpler. We have a left and right bound. They're both inclusive, so that means both of these brackets are square. So that's the range. Okay, let's do the domain now. So now we're only looking horizontally left and right. So we know that we started as far left as 0. So again, the domain, this is the independent variable, that's time. So this is like the x value, but it's t instead. Okay, so the problem is we don't know exactly how far to the right it goes. We know it's somewhere between 3 and 4, but we need to figure out more precisely where that is. So this is where that equation actually comes into play. So we know that the distance traveled at any given point is our average speed times the time. Okay. Well, we're looking for what time, okay, is necessary such that the distance traveled is 200, because that's where we max out. So I'm actually going to substitute 200 for d, because that's the distance we travel, and I'm just going to solve algebraically for t. So at what time did that occur? So to isolate t, I just divide both sides by 60. Okay, and those of course cancel, and you get t equals, and if you use your calculator, but you actually don't need to, you can reduce this, you will get 3 1/3. Okay, this is in hours. So this would be 3 hours and, well, what's a third of an hour? That's actually 20 minutes. So if you look at your graph, that would seem about right. After 3 hours and 20 minutes, that's when you'd have to recharge the battery. Okay, but I'm just going to leave it in this format. So let's do our number line notation. Okay, we go as far left as 0. Okay, that's included. And we go as far to the right as about 3 1/3. Or 3.3 repeating. And of course we can have any time in between there. So there's our number line notation. So I think it's pretty simple to go to set notation now. So we'll make the curly brackets. So the domain is all values of t such that I'm larger than 0 or equal to 0, but I'm less than 3 1/3, 3 hours and 20 minutes. Inclusive. And it's continuous again, so t can be any real number. All right, so let's finish off. Interval notation, same as before. So we go as far left as 0, and we go as far right as 3 1/3. Both endpoints, we included them, so that's why both of these brackets should be square. All right, last example, the domain of some linear relation is given by, and we're told that all the x values are greater than or equal to -3, but less than or equal to some number p. The important piece of information is actually right here. We're told that x, they can only be integers. Okay, so we're only dealing with whole numbers, either positive or negative. We're told the range, however, and it's in order, and it's actually just a collection of 5 different numbers: 4, 7, 10, some number q, and the number 16. The question just wants to figure out what are the smallest possible values of p and q. Well, I would argue it's actually easiest to determine q first. Okay, we're told that they're in order, so this is a increase of 3. Okay, that's an increase of 3. And we're told it's linear. Right? So because x is increasing, okay, these can only be integers, they can only increase by one whole number each time. Okay, so if x increases by 1, y has to increase by 3, and that pattern has to remain consistent. If it breaks, then it's not a linear relation. Okay, well, I think it's obvious now that q has to be 13. Okay, all right, but what's p? Well, this is a linear relation, so each value in the domain has to be matched with one of the y values here. Now you may think, oh, there's infinitely many numbers in here. Well, they're not actually. Thank goodness. If this was an r, we'd be in trouble. But because this is a z, we can actually list this as a more concrete set. Here, I'll just write that here, right below. Okay, instead of writing it like this, I'll just write all the numbers that I'm allowed to use. I'm allowed to use -3, and I'm writing them in order. -2, -1, 0. Now, I'm only allowed 5 because there are 5 in here. So the fifth one here would have to be 1. Okay, well, obviously, that's as high up as I can go. There we go. So, P, you're going to write. So P is 1. Okay. Now, though we're done, just go one step further, and I'll actually write out the ordered pairs so you can actually see the numbers matched up within their corresponding sets. So if you were to actually plot this in a graph, okay, this is not an interval, these are actually coordinates now. So the first x coordinate was -3, so that gets matched up with 4. Okay, the next one up, remember we can only use whole numbers, positive or negative, so this goes up to -2, and that gets matched up with 7. So I'm just writing all the ordered pairs. The next one is -1, that was with 10. Just move over here. Next one was 0. Okay, that got matched with Q, which we determined was 13. And then our last one has to be 1, and that gets matched up with 16. Right, so that was the P, and this is the Q. So if you plotted all 5 of these points on a graph, they would form a straight line.